Hello everyone, thanks for attending to my presentation. So in this talk, I will walk you through the inversion of fracture aperture distribution from the permeability and velocity relations. I will start off by giving a background of this study, and then I will mention about the terminology of which the inversion is conducted and how the overall workflow works. And after that, inversion result and the associated uncertainty will be presented. And at the end, I will provide a conclusion to this talk. So the motivation for us to do this study is that the flow properties and also elastic properties in the rocks are to a large extent the geometric dependency of the porous volumes. So in a simplified picture, consider a single rough fracture where the surfaces are rough in nature and they are correlated in vertical topography. In this case, the relative surface roughness is going to provide us a distribution of fracture open spaces, or what we call apertures. And these surfaces, when they are subjected to normal stressing, the distribution of these spaces will change distinctively, and the open volumes will provide the capability for the fracture to conduct fluid and also electricity flows. And at the same time, the stress-free volumes of these fracture apertures, together with the contacted area subjected to normal stressing, will provide the elastic properties of these fractures. And in the flow elastic story, we can have a lot of quantities to describe the flow and elastic properties of fractures. For instance, we can describe it in terms of the fluid permeability, electrical resistivity, and also the transport characteristics. And for the elastic properties, very often we are talking about the wave propagation velocity, and on the static case is the fracture specific stiffness, and also an attenuation effect for the dynamic wave propagation. So the understanding of the relation between fracture aperture distribution to the respective flow and elastic properties is considered a forward problem. And if we have well enough understanding on the forward problem, then the idea is that can we tell from the flow and elastic properties how the aperture actually distributed in the medium? So this is our inverse problem, and this is exactly what we want to address on in this topic. And it all starts with the ability to quantify each of the perspectives. For instance, the fracture aperture distribution have randomness in nature, so we have to adopt a certain statistical representation in order to describe how the spaces are actually distributed across the volume. For instance, if we consider the fracture surfaces are actually barely in contact, so we can obtain a first contact aperture, and we propose to describe it in terms of these parameters. First, the autocorrelation length, describing the spatial autocorrelation of these aperture heights. And the other parameter is the root mean square relative surface roughness of fracture surfaces, denoted by sigma. So this parameter is going to tell us how variable overall the aperture heights are in a particular single fracture. Moreover, we are going to assume the single fracture apertures are following normal distribution as indicated by a lot of experimental results. The advantage of parameterizing single fracture apertures is that we can numerically easily synthesize artificial fracture apertures using Fourier increment methods. And this parameterization is demonstrated to be reliable on capturing the permeability decline trend over static fracture compressions. So this is our workflow. So this is going to be a case study. We are going to base on our investigation on an artificial fracture in a granite rock. So by doing experimental measurements over the various compression states, we can obtain experimental flow elastic relations. That is going to be our target on which the inversion is conducted. And the other side is that the inversion has to incorporate with numerical simulations. So by defining a wide range of roughness parameters, we can numerically synthesize for different numerical single fracture apertures, on which we can perform numerical simulations to conduct their respective flow and elastic relations. And we have experimental and simulated relations for fracture of a wide range of geometric characteristics, and we can approach for the most consistent trend in order to solve for the best set of roughness parameters that describe our artificial fracture. And since this is an experimental study, we can also obtain a digital profile from our artificial fracture, on which we can obtain the true answer of the roughness parameter based on statistical analysis. And at the same time, if the experimental result is not sufficient or has noise contaminated, the digital profile will be able to provide supplementary information on assisting us to construct a well-defined experimental flow-elastic relations. And in this study in particular, we are going to represent the flow property with effective permeability of the fractured rock, and the elastic properties with p-wave velocity. Let's start by introducing our subject of study. So this is an artificial single fracture created by Brazilian splitting across the radial direction of a granite core. So the result is that we obtain a single fracture of length dimensions of 76 mm and 35 mm respectively. And we can obtain the surface topography of this single fracture using laser altimetry scanning. And then we have obtained this profile in the spatial resolution of 0.2 mm of digital resolution as our digital profile. And from this digital profile, we can derive our single fracture, the first contact apertures, as shown on your top left figure. So this from this aperture map, we have observed that the single fracture aperture actually does describe pretty well with a log normal description. For instance, the log normal approximation manages to capture the peak of aperture height and also the characteristic that the distribution is flat-tailed. And the two figures on your right shows the power spectral density distribution in x and y directions respectively. And the autocorrelation length of fracture aperture is defined as the twist between two tracks is shown in the power spectral density. And in this case, we managed to pick the value of 3.8 mm and 2.9 mm as our autocorrelation length in x and y direction respectively. And the root mean square relative roughness of this fracture is shown to be 0.2 mm. So this is something we can derive from our digital profile. And experimentally, we conduct the flow measurements using steady-state volumetric flow rate measurements. So we try to inject water at 20 degrees Celsius with 2 megapascal of hydraulic pressure difference on a confined fractured core, and the flow is driven in x direction as shown in the figure on top. So we measure the 30-minute average flow rate across the fracture under a given confining pressure, and we repeat the experiment under increasing pressure. So at the end, we can represent the flow capability of the compressed fracture and interpret as the effective permeability with the cubic law. So the figure on your right bottom is representing the experimental result. So it's shown that as confining pressure is increasing from 5 to 25 megapascal, the permeability of the fracture decreases from 7 Darcy to a fraction of a Darcy. In this experiment, the measurements of dynamic elasticity is insufficient, so we have to basically supplement this information using modeling. So the idea of predicting p-wave velocity across the core is that the dynamic compliance of rock is basically contributed by open surfaces of apertures. And based on this philosophy, we can estimate the velocity using a crack model. In this case, we are approximating the behavior with Hudson-James model from the digital fracture profile. So we can view fracture apertures as with volumetrically equivalent collections of ellipsoidal cracks which are very thin. And assuming these cracks doesn't change its aspect ratio under fracture compression and the host rock is homogeneous, then we can compute the p-wave velocity with the effective moduli C33, and the result is shown here. So It's indicating qualitatively indicating that as the effective pressure is increasing from 3 to 23 megapascal, because 2 megapascal comes from hydraulic pressure, the P-wave velocity is estimated to be between 5,582 to 5,598 meters per second. So based on these informations, we can construct our permeability and VP profile. And because of the involvement of a modern input, and also there may exist systematic differences due to experimentation, so we are not going to take the absolute value. Instead, we are going to normalize the respective values with respect to the lowest measured pressure level. In this case, that's 3 megapascal of effective pressure. So this will serve as our target profile, and we will find from the numerical simulation that which set of profile is going to be closest to our target profile, and this will be our inversion approach. So the job here is to search for the symplectic profile that has the most consistent trend on permeability and P-wave velocity. So in numerical simulations, since we have the true value of the roughness parameter, we can devise a range of simulation around the true figures. So we're going to numerically synthesize aperture distributions of lambda x between 3.4 to 4.4 millimeters, lambda y between 2.4 to 3.4 millimeters, and sigma between 0.175 to 0.225 millimeters. And for each set of these parameters, we're going to conduct 50 randomness realizations, and each set of generated apertures will undergo simulations of fluid and elastic properties. And for effective permeability, we are going to simulate with the Darcy's law with the local cubic law assumptions. P-wave velocity with Hudson Chains model as usual. And the effective permeability on the fracture will be approximated by the asperity contact model without consideration of asperity interactions. So among these 50 realizations, the simulation results of these realizations, we are going to bootstrap the results for 1,000 times in order to obtain the mean and the standard deviation of the randomness realizations better. So this is an example of the simulated permeability and velocity profile using the true roughness parameter 3.8, 2.9, and 0.2 millimeters. So on your right, you will be seeing how the generated aperture actually looks like for different randomness seedings, but all of them shares the same roughness parameters. And the profile here, the solid line represents the mean of all the realizations, while the error bar is showing you the one standard deviation discrepancy for permeability and also velocity respectively. And we can see from here actually most of the discrepancy actually shows up for the permeability instead of P-wave velocity, which has really minor uncertainty. But this is because the permeability of a fluid, especially when the fluid is driven in one direction, is heavily dependent on the connectivity of the aperture heights. So it's not only the overall aperture height that matters, and also the connectivity of these cases matters. So this is why we need to consider many randomness realizations. So we can conduct our inversion either following the mean of all these results, and we can at the same time we can also consider a different degree of uncertainty. And the red dotted line on this figure is actually giving the profile that's following 1 SD above and also 1 SD below the mean estimation. So we can start by considering the mean ensemble behavior of this profile. So if we use this profile, the terminology is that we're trying to minimize for the discrepancy between the normalized permeability VP trend here. So we are going to evaluate for the distance between experimental datum to the simulated relations as a single discrepancy using simple Euclidean distance. So we evaluate for the distance between each point on the target profile to the simulated profile, and we sum the results for all the experimental pressure level. And then we try to minimize for the total discrepancy as defined by the total distance across all the experimental level, and that would be our inversion result to approach for the profile that has the least discrepancy. And it would be interesting to draw your attention to what does that mean if I define our objective function in this way. Basically, the first point is always has the distance of 0, and since permeability can span an order of magnitude or 2 orders of magnitude, while basically p wave velocity is roughly remain in the same order of magnitude. And the equation is basically telling you to trust more on the information of low pressure datum, because that any difference will be an order of magnitude higher than that of the high pressure condition. So basically that's what that means. And our inversion result following the mean of simulation profile is giving us an answer of sigma will be 0.185 millimeter, while lambda x is 3.8 millimeter and lambda y is 3.4 millimeters. So it seems that we managed to capture the lambda x characteristics and at the same time underestimated the sigma a little bit. But it is a pretty good result in my opinion. And we can also look deeper into the problem of what happens if we consider the numerical simulation estimate of with plus or minus 1 SD uncertainty. So we can repeat the inversion terminology with the profile of the different uncertainty level. For instance, here I'm doing basically from negative 1 SD to plus 1 SD in the interval of half an SD. So the red dotted line on this figure shows you the true roughness parameters, while the black dots is the inversion result using respective profiles. So for lambda x, it shows that for most of the cases it's inverting for a range between 3.6 to 3.8 millimeters. For lambda y, we consistently overestimate, but then at the same time it shows to be a bit inconclusive because it's jumping up and down. Basically, it's telling you any value in this range is going to give you pretty good fit, basically above 3 millimeters. And for sigma, most of the cases is inverting for the value between 0.175 to 0.19 millimeters. Well, of course, occasionally is suggesting that a higher value is going to fit the profile as well. So these are the uncertainty we were seeing by giving rise from the different randomness realizations in our aperture genesis. So this problem is inverting for 3 parameters in total, but what happens if we can reduce the problem to inverting for 2 parameters only? The idea is basically that since the experimental flow is driven in x direction, so presumably there will be less information for y directions geometries. So we can basically see what happens if we have the lambda y fixed. In this case, we are going to fix at the non-true value, which is 2.9 millimeters, and conduct the inversion again. So this is the result showing you, okay, it seems that the true lambda x is going to be estimated around the mean of all the numerical ensembles. And well, and at the same time, 3.6 to 3.8 millimeters seems to be a pretty a good uncertainty range for our estimations. And for sigma, is at the same time is still a bit slightly underestimated, between 0.175 to 0.19 millimeters. So basically, from this exercise, we can estimate it that our confidence is probably lambda x between 3.6 and 3.8, while sigma is between 0.175 to 0.19 millimeters. So in conclusion, the idea of this project is based on that pressure-dependent flow-elastic relations are controlled by the fracture aperture geometry, and that's why we can use these relations to know and reflect the geometric informations. We have explored for the possibility of doing fracture characterizations with permeability and VP relations, and the whole exercise is based on the ideas that statistical descriptions of fracture aperture distributions has to be imposed to quantify the randomness, and the experimental measurements are conducted under static conditions under increasing loading, and the numerical simulations are based on first order physics, and we managed to get a pretty good fit of aperture distributions by using these simple informations. So I guess this is giving us an idea that the pressure-dependent flow-elastic relations has potential of being used for fracture characterizations. So thank you very much for your attentions and interest in this study. So for more questions and you wish to have more information, please feel free to contact me at this email address. So thank you very much.